Welcome to the Demography Today lecture series, sponsored by the BBVA Foundation and co-organized by the LOMPOP project and the Spanish National Research Council. And we have the pleasure to have today Professor Peter Atkinson, who is the Dean of the Faculty of Science and Technology at Lancaster University and Dean of the Faculty of Health and Medicine at the same university. The main focus of Peter's research is in remote sensing and spatial data science, including spatial and spatiotemporal statistics and machine and deep learning, applied to a range of environmental and socioeconomic phenomena. His most significant research themes include vector-borne disease transmission systems, including trypanosomiasis and malaria, global vegetation phenomenology, and his response to climate and anthropogenic drivers, natural hazards and their impacts, including flood modeling, landslide susceptibility mapping, and near-Earth object impacts, and image downscaling and image fusion based on explicit models of the space-time sampling framework. He has published more than 270 peer-reviewed articles on these topics in international scientific journals, led multiple large grants and supervised around 60 PhD students, authored one book and over 50 refereed book chapters, edited 8 journals, special issues, and 8 books, previously editor of the International Journal of Remote Sensing Letters for 9 years, and currently associate editor for Computers and Geoscience, and sit on the editorial boards of Geographical Analysis, Spatial Statistics, International Journal of Applied Earth Observation and Geoinformation, and Environmental Informatics. And as you can guess, he's incredibly busy, and we are so lucky to have him here just for a few hours in Madrid. But we took the opportunity that during the few hours that he is here, he's giving us one of the Demography Today talks. So as usual, we have 45 minutes to 1 hour, and welcome to Madrid.
So thanks very much for the kind invitation, and thanks for inviting me to come over today. It's a pleasure to be here in Madrid on this beautiful day. I'm going to talk to you today about handling hospital and health facility data in Africa, in sub-Saharan Africa in particular. And I hope that this talk is relevant to each of your subjects that you're studying or working on. If there are any questions as I go through, do shout out. I'm very happy to sort of interact and take any questions as we go through. So the sort of central tenet of the talk is that there are a lot of health case data becoming available in Africa and other countries across the world, and it represents a fantastic opportunity to handle those data, to explore the data, to find out what's going on in the data, and to help with health services to intervene in order to reduce the burden of disease. So that's the sort of central tenet, and the solution that we work on, but that we provide, is to use space-time statistical methods, and I'll try and explain what's going on with those statistical methods without going into any detail. I don't think there are many equations in this talk, but it's important to get an idea of what's actually going on with those methods. Now, this is me. I'm at Lancaster University. This work was done by a very large number of people. A lot of what I present was primarily done by Victor Alagena, who's working now at KEMRI in Kenya, in Nairobi. But there are many other people, and some of those people are sort of shown as authors on papers as we go through. So I'll refer to them, or try to refer to them as we go through. So if we step back and think about what's happening with what types of disease transmission systems we're interested to analyze, this diagram tries to categorize them into 4 different types. So on the left, we've got diseases or disease transmission systems that don't involve vectors, and on the right, we've got disease transmission systems that involve vectors. These are either flies or mosquitoes or bats or some other sort of vector that transmits the disease from one organism to another. So on the right we've got vector-borne systems, and on the left we've got systems that don't involve vectors. And then the top ones are anthroponoses, whether that's direct transmission or indirect transmission via a vector. And the bottom we've got zoonoses that involve animals. So the disease either transmits across animals and then through to humans, or there's a cycle that involves animals and vectors and then goes through to humans. The disease that I'm primarily talking about today is malaria, and that fits into this disease transmission system up here. So there are no animals involved with malaria, but there are vectors. That's the mosquito. And a fundamental part of what I'm talking about today is the link between vectors and the environment. That because the vectors often have a strong link through to the environment, that means that we can use data sets such as those acquired from remote sensing, which are very commonly available, easy to get, easy to download, easy to analyze those data in order to get variables that relate to habitat, for example. Then we can link through to the disease vector. And that's a sort of another central part of the argument. So that can help with mapping these diseases. Because if we can map the vector, then that helps with modelling the disease overall. So another thing that I wanted to say by way of introduction is to differentiate between the term prevalence and incidence, because what we're going to be looking at in this talk is primarily incidence or incidence rate. Incidence is the number of new cases that appear within a certain period of time per certain number of the population. Whereas the prevalence is a snapshot, so just a cross-sectional survey across the population at a given point in time. What's the number of cases in the population? So it's illustrated by this diagram, which shows that if this was the population, then if we took a prevalence snapshot at this point in time, then there would be 3 cases, 1, 2, 3 here. And if we took a snapshot here, then there would be 2. And that would be the prevalence in the population at that point in time. Whereas the incidence is the cumulative number of new cases that arrive in the population over this period of time, in which case the incidence count here would be n equals 14. Does that make sense? So there's a difference between incidence and prevalence, and what we're looking at today is incidence. Now, the data sets that I want to talk about come from various sources, but the primary one is the Health Management Information System data sets that exist across many countries in sub-Saharan Africa now. In the past, when we started working in Africa about, 2006, so about 13 years ago, many of the HMIS were recorded on paper. So they looked like this. They were just sort of records of cases that had occurred. And then there was reporting up to the sort of district level hospital, etc. But over time, increasingly, these data have changed from paper records to being digitized so that they're available on computers and we can access them and analyze them, which is a massive transformation occurring across many countries. But importantly, the facilities are also geolocated. So people have gone and with a GPS and recorded the locations of the different health facilities, the hospitals, the dispensaries, etc. So we've got a picture of where the facilities are, and we've digitized the counts of cases that are occurring in these facilities. This shows what the data might look like across sub-Saharan Africa. So don't worry too much about this part of the diagram, which is a map that's produced using these sorts of techniques. On the right, in the black dots, they don't look like black dots, it just looks like a surface because there are so many of them. But these dots actually represent the facilities across all of Africa, or all of most of sub-Saharan Africa. And each one of those dots represents a record of cases that are recorded at facilities and reported. And these are reported on a monthly basis. So if we take one of these I think districts in Namibia, which is this country just here, then we get a time series of counts on a monthly basis for each one of those districts, which is basically the aggregation of all the point data within that district or province or enumeration area. So for Zambezi, you can see that the count goes up to about 500 in 2014 from 2012. For Kavango, the number goes up to about 3,000. So this area here, Kavango, the number goes up to about 3,000 cases into around early 2014. Does that make sense? So that's the kind of data that we're dealing with, which looks like, they're spatially point data, but a time series, so varying through time. So that's useful. But look how many there are. These are most of this is public sector health data cases for most of Africa. And that's an incredibly important data set, an incredibly important opportunity. Because the facilities are geolocated, we know where they are, and that means that we can use space-time statistics to start to analyze these data. So a count of cases is one thing. For many applications, what we're really interested in is the rate, or the number of cases per 1,000 of the population over a given period of time, like an annual period of time. Because that normalizes for the population. If you had a count of 4 in one area that has, say, 100 people, then that's a very different meaning to a count of 4 in an area that has 10,000 people. So the rate is the incident rate is what we're really interested in for many applications. However, we don't really know what the population is that the count is being drawn from. So each facility has a catchment, and draws and the people within that catchment will tend to attend that facility, but we don't know what that catchment is, and we don't know what the population is that sits within that catchment. So this is a much harder problem than at first it seems. So we've got these fantastic count data. What we haven't got is the denominator of the rate. In other words, what population are the counts coming from? So there are many problems with these HMIS data. One of them is non-reporting gaps. So when we started working on these data in 2006, the reporting rate of the data set for Kenya that we were working on then was 46%. So in other words, 54% of the time, there just wasn't a report. So lots of gaps in the numerator, in the cases. So part of the reason was that if the number of cases was very small, like 0, then maybe they didn't report that, just felt that that wasn't worth reporting. But actually knowing that it's a 0 is important. A big issue is underutilization. So it turns out that if people live far away from a facility, then they may not attend even if they're ill. And that's potentially with a fever that could mean malaria, which is obviously a hugely serious disease. And but it turns out that geographical access is a barrier to attendance, and that means that even if we know the catchment of the facility, people that live far away within that catchment may not attend, even if they're ill. So we need to account for that. There's a difference between clinically confirmed or clinically diagnosed and slide confirmed diagnosis. So if there can be a tendency to overdiagnose through a clinician, because if there's a fever, then it's better to be conservative, to administer the drugs, make sure that the person is treated, even though it might not be malaria. So there is a tendency to overdiagnose, and that's a problem within the data. And then there are support effects. So I'll need to pause and explain what the support is. The support is the area that an observation is made over, or that a measurement is made over. So if you think about remote sensing, the image is made up of pixels. So each measurement is made over a pixel. That's the space over which a measurement is made. So there are, as we change the support, as we change the area over which we make a measurement, the data change and the variation changes. So we need to account for that in these models. Okay, so this represents a sort of generalized approach that describes the sort of things I was just talking about. In the top part of this diagram, we estimate the malaria cases as the combination, as the sum of the confirmed cases, those that are blood confirmed, so we know that they're malaria, and those that are suspected, in other words, clinically diagnosed, multiplied by a test positivity rate. And that gives us our malaria cases. This is the numerator in our incidence rate equation. In the lower part of this diagram, there you go, we've got the catchment population that use the health facility. We need to estimate this, and I'll talk about that a bit in a minute, times the reporting rate. So in other words, if people don't attend, then we need to take that into account. And when we multiply those two things together, we get the expected number of cases, and we can use the numerator, the malaria cases, and the denominator, the expected number of cases, in a space-time statistical model in order to estimate incidence rate, or actually to estimate incidence, but the rate is in the equation because the count is on the left-hand side and the expected case is on the right-hand side. Okay, so that's the introduction. I hope that sort of gives you some context to what we're trying to do here, is to handle these HMIS data. Lots and lots of potential, and requires careful handling through statistical models in order to achieve results that are useful. So the first case that I'm going to talk about is trying to work on this denominator, trying to estimate the catchment population that would attend a facility. And this was published in 2012 by Victor and other people that I worked with, including Jim Wright and Bob Snow in Kenya and a few other people there. So this diagram shows the distribution of the health facilities in Namibia. I should have said that this test case is for Namibia in southern Africa. The blue dots show you the locations of the public health facilities. These are the hospitals, the dispensaries, the health facilities. So you can see that there's a fairly wide spread of these health facilities. I think there's over 300 of these across northern Namibia. The red dots represent something called a malaria indicator survey. And these are also spread across the area spatially. And the malaria indicator survey, or MIS, was used for a different reason than the public health facilities. And I'm going to explain what we did with the MIS data now. So the MIS data gave us a response to a survey question, which was, when you had fever, did you attend a facility or not? And the question was as simple as that. But we know the answer, 1 or 0, and the answer spread spatially, because we have those spatial data that I just showed you in the map. So what we wanted to do was to connect that answer, yes or no, I did or did not attend a facility when I was ill, or when my child was ill, to the time taken to travel between the place that they live and the closest facility. So in order to do that, we needed to create something called a cost surface, which is just a map that shows you how long it will take to get from any one location to a facility. And in order to create that cost surface, we had to know we estimated the travel times across different types of land. So included in this were different types of land use and land cover. We included roads of different types, rivers which were not crossable. So the travel time across water was 0, you couldn't do it. And we also included a digital elevation model. So you can see that here, tree cover, broadleaf, deciduous or evergreen has a speed of 5 kilometers an hour. So you can walk through this at quite a fast pace. Whereas something like herbaceous cover, you tend to walk more slowly through that, and then bare areas or desert, 2 kilometers an hour, so slower. So we estimated these travel times from the literature and then used them in order to create a cost surface based on maps of land cover, knowing where the roads were, etc. The different type of roads are primary roads for which the speed is 80 kilometers an hour, assuming that people drive or can get a bus. Secondary roads 60 kilometers an hour, and then tertiary roads 10 kilometers an hour, assuming cycling. So there were a few assumptions in here, which are testable, but it's a good starting point based on, as I say, values from the literature. So, given the gridded data sets of different land covers, the roads, rivers, etc., knowing the travel times or speeds across these different land covers, the locations of the health facilities, we were able to create a cost surface. And then, because we knew the travel time from any location and the answer to the question, did you attend a facility or not, we were able to put those two things together and work out how the probability of attendance changed as the travel time became larger and larger and larger. So if you look at the x-axis here, the time is increasing from 0 to an hour to 2 hours to 3 hours, 4 hours, etc. as we go along this x-axis. And you can see the 1 was yes, we attended a facility, and the 0 is no, we did not attend a facility. And the ratio between these two changes as the travel time becomes greater. And what we did was fit a 3-parameter logistic model to this data set. So it starts at a positive, but not a value of 1. Starts at a positive value and ends up at a positive value. And then there's a sort of a rate of decay between the two. So there's a sort of meaning to this, which is quite important. It means that if you're right next door to a facility, you don't necessarily attend, even if you're ill. So that's odd, and takes a while to get your mind around what's going on there. Then the rate of decay is such that, say at about 3 hours, so 180 minutes, the probability of attendance has decreased to 0.55, something of that order. And that's quite a shock. That's shocking to me, that the probability of attendance would go down to a value as low as that at just 3 hours away from a facility. And it continues down to a value that's less than, that is about 0.15, I guess, at a distance that's maybe 12 hours or 15 hours. These really low probabilities of attendance, and these come directly out of surveys that were asked in the Malaria Indicator Survey. So when we map the probability of attendance using that logistic curve, and given the facility locations, we can see what happens to the probability of attendance spatially. And these areas out here, which are primarily rural areas, the probability of attendance is very low. So what's been done in this part of the analysis is we've estimated probability of attendance, and we can show what that looks like spatially based on a cost surface analysis and the Malaria Indicator Survey question. to use these data in the incidence rate calculation that I was talking about earlier, we need to intersect this probability of attendance surface with a map of the population, with a detailed map of the population. And we have a map of the population from WorldPop, or what was called AfroPop, on a 100-meter grid resolution. So we're able to intersect the two together and then use it as a denominator in that incidence rate equation. Okay, so we've got the malaria cases. We're able to get an estimate of the denominator in order to estimate expected cases. And we can put this together in a statistical model, and that's what I'm going to describe in this second case. And this CAR means conditional autoregressive model, and I'll talk a bit about that so you know what that is in a minute. This work was done by Victor again, and some of the same people were involved, Jim and Bob Snow and Noor, and several others were involved in that. We published this in Spatial and Spatiotemporal Epidemiology in 2013. So we go back to this map of Namibia, and this shows you now the observed cases. This shows you two things. As before, the distribution of the facilities, so the hospitals and the health centres and the dispensaries, but it also shows you the number of cases through the size of the dots on the plot. And the number of observed cases goes from 0 to 1 up to 101 to 165. So, and you can see how those are distributed. You can see there's some large values in these areas. Kavango, what's called Caprivi, I think it was described differently previously, as Zambezi, and Omusati here. So the issue is that these data, as I said before, are recorded as cases. They're also recorded as a time series. So we can get those time series plots for each of these points, but what we can't get is a map. There's no sense in which we can get a map. Why is a map important? It's important because we need to know where the cases are actually arising in order to intervene. So the sort of driver behind all of this work is spatial targeting of interventions, if that makes sense. So that the cases don't happen in the hospitals; they happen out somewhere in the where people live, where people work, etc. People get ill, and then they present at the hospitals. So these data are useful, but they don't really visualize or tell us where the hotspots, where the high values are occurring, what time of year they're occurring, etc. So they're quite limited as they are, even though they've been digitized and geolocated. So this describes the model that we applied. It's a Bayesian. We used Bayesian inference because we fitted it in a sort of approximate Bayesian package called INLA. But it's basically a mixed model that has linear effects and spatial and temporal random effects. So this is not too important, to be honest, but the fixed linear effects are here. So this Z is a covariate, which means it's an explanatory variable, which we know everywhere at a given support. And beta is just a parameter. And then we've got we've got spatial random effects, and which are represented actually by this term, and some temporal effects, which are represented over the whole area, so seasonal effects, and all of these are additive. And this E here represents the expected or log of expected cases, and mu is just the intercept. So the usual regression model would just be this part here. It's a Poisson model, so we have the expected number of cases on the right-hand side, and then we have some spatial and temporal random effects also. And the CAR model is the spatial random effect. It just means that we use neighbouring predictions in order to inform the prediction itself, and that iterates back and forth. Well, okay. So as I said, the predictions were made using R-inlet. The predictions were made to all facility months, so all spatial points and all months, and then aggregated up to administrative 1 level in the census. And this is what we get. So given those point data that I showed earlier, we're able to run a space-time statistical model and estimate the incidence rate, as in the incidence per 1,000 of the population, and show that spatially. And you can imagine that if you're working in the Ministry of Health in Namibia or in some administrative capacity, then knowing what the incidence rate for your administrative area is very helpful to you. And also, if you're the government, then you can look across spatially and work out where resources need to be deployed in order to make a difference on the ground. However, because the predictions were made to all facility months, we get a time series of estimates and a seasonal pattern, which is also important, because interventions, one of the things that became important more recently was temporal interventions, so seasonal prophylaxis, intervening early in the season, for example, or during the season, in order to make sure that drugs are not administered when they're not really, or not available when they're not needed, and are made available and accessible when they are needed. So you can intervene at the right times to make with the greatest efficacy and the greatest efficiency in terms of utilization of drugs. Some of these drugs, like Coartem, are expensive relative to drugs that were available previously. So it is important to use them effectively. So we've been able to make estimates for all facilities. The second line here is completely wrong. We can't make, in this model, predictions for all pixels, so sorry about that. We make predictions for all facilities, and then when we aggregate those, we can get estimates for districts or the whole area. So this this plot here shows you the seasonal pattern of malaria incidence, the incidence rate, in northern Namibia. So let's go through it carefully then. The number of cases, the raw number of cases is shown in these grey bars. The crude incidence is shown by the green bars, and the cases per 1,000 population is the scale that represents this green bar. And then the model is the model prediction is the red line, the red dotted line, and then the confidence or credible intervals around that estimate are shown in the lines above and below that main line. Clearly, there are differences between the crude incidence and the predicted incidence, but those differences are important and come about because of the statistical modelling. And in a sense, if you didn't have the statistical model in order to inform and glue things together, then you would end up using crude incidence, which has issues and problems in it that haven't been dealt with. What's important, I guess, is that you can see the seasonal profile of malaria in Namibia, which is that there are high values of incidence in January, February, and March, April, and then declining to low values in the in our northern hemisphere summer, and then it picks up again in December. But we can disaggregate this in space and time. So we've seen the map of, where's it gone? There. Mean incidence here. So we get spatial estimates over these administrative areas, and then we get a temporal seasonal pattern for the whole of northern Namibia. But because we've estimated at all facilities, then we can aggregate these on a monthly basis and for the administrative areas. So we can see how malaria incidence is changing, not only through space at one time and time at another time, but through space-time. And you can see that, again, it's obvious that January, February, March and April are high months for incidence rate, with the other months being lower. But also you can see that the incidence rate in the southern part of northern Namibia remains high through most of the year, whereas in the very northern part of northern Namibia, it's high for those 4 months and then decays to a much lower value. So that's really useful in terms of targeting interventions in space and time. Okay, so that was dealing with the denominator. That was case 1. Case 2 was putting the numerator and the denominator together in order to estimate incidence rate. And because we're handling the data in a particular way, we can get out space-time estimates. I'm now going to talk about a thing called change of support, which means effectively zooming in. This was published in, I think it was 2016, sorry, in Scientific Reports. And this is what I mean by change of support. So upscaling is becoming more and more aggregated, and downscaling means zooming in. And what we want to do is to zoom in order to get fine resolution maps, where the resolution of the maps is finer than any of the input data, whether it's the data points or the districts or whatever. So that's the sort of what's going on in this part of the talk, is trying to zoom in. So we built this bivariate or joint model, a joint distribution model, which it's joint between two scales. It's joint between the pixels on one hand and the districts on the other hand. So it allows upscaling and downscaling between the two scales, and the output as a byproduct of the model is a fine resolution map. We used the same case data from 2012 to 2014 that includes public facilities and private facilities, so 90% public, 10% private, and there are 20,689 cases in this data set from 322 health facilities. Now this is a nice diagram that helps to explain what's going on. It's probably the most important part of the talk, to be honest. So let's go through it carefully. On the left, top left, in the top left diagram, you've got a series of things that I need to explain to you. So the first is a dispensary, which is here. The second is a hospital, which is here. And then in red, we've got houses with malaria cases. And in black, we've got houses with no malaria cases. So the malaria is here and here and here. This is a main road, and we've got a river, and I'm not sure what the blue dot is, the blue dotted line is, but that's a marsh, supposedly. So that's the sort of scenario that we're dealing with, and we've tried to sort of illustrate a typical scenario. You can see that there's a hot spot here, which is in red, because there's a cluster of 3 houses with malaria cases. Now this diagram here in the lower left illustrates, I think, really, really nicely the problem and what we've tried to do with the data. So we've got case data for the hospital and for the dispensary. But in this area, there are 2. There are 2 points at which we are recording cases, just 2 points. But we're interested in the whole area, right? We're not just interested in 2 points, we're interested in the whole area. What we do get at the hospital and the dispensary is a time series. And you can see how the number of cases is changing through time at these two places. But these are cases, and they don't take into account the population that this hospital and the dispensary are serving. So in order to make sense of these counts, these count data, We need to know that population that the facilities are serving. So this top right part of the diagram shows the probability of health facility use for fever treatment decaying away from the hospital and the dispensary in the way that I explained before. You know, that sort of 3-parameter logistic model where we model this probability of attendance as people got further and further away in time from a facility. So that represents that sort of process that we need to estimate. Back to this lower left diagram, we've got some vegetation, which is represented by a thing called the EVI, or Enhanced Vegetation Index. It's a remotely sensed variable. We can measure it from space, and we calculate the EVI as a ratio, and it represents greenness. So we measure the greenness of the vegetation. And of course, as I said before, because the mosquitoes, the vectors of disease, are constrained by the habitat, so they need to be close to water for egg laying, etc. They tend to be close to vegetation, depending on what part of Africa, etc. And the marsh here is probably an important part of explaining the distribution of the mosquitoes. We need to use this fine resolution information on vegetation, etc., in order to constrain the likely distribution of the mosquitoes and therefore the disease. So what we've done effectively through this integrated modelling is to take 2 data points and to produce a complete map of incidence rate. So you've got incidence count at these 2 points. That's all you've got. And then through statistical modelling, involving EVI as a covariate, involving this knowledge of how the probability of attendance decays away from facilities and its intersection with knowledge of the population, we're able to integrate all those data sets and get out a map of incidence rate effectively from these 2 data points. And that's really important because without the statistical modelling, they remain 2 data points. And across Africa, you know, thousands of data points. But you can't use them to inform where to target interventions in the environment. So the outcome is a fine resolution map of incidence rate, where hopefully the incidence rate is predicted to be high where the hotspot exists. Okay, so this shows you a sort of a typical process or a conceptualization of a process that people go through. So we start with the population. If you're not infected, then you just carry on in the population. There's no fever. If you are infected, then the infected people will have fever and present at a facility. So they will seek treatment, probability of fever treatment seeking. They enter the formal care system and present and become a confirmed case if they have malaria. And then it's these cases that we model in this joint distribution model. And I guess the important thing is this link between scales. So we've got a link between the district scale and the pixel scale in order to be able to downscale and go from one scale to the other. And the objective, as I said before, is to spatially and temporally target the population at risk. So when we go through this process of downscaling, we get out now fine resolution maps of incidence rate. So previously I was showing you maps that are produced across districts or administrative areas as averages. But now we're able to zoom in beyond the administrative boundaries and actually produce continuous maps of incidence rate on a pixel by pixel basis. So it's a kind of magic. So you can see how the incidence rate is changing through time from January, February, March, April through to December. And you can see how it's changing spatially. So if you look at this area in March, you can see that there is some spatial variation. I think the temporal variation is dominating. Yeah, temporal variation is dominating, but there is some spatial variation, and you can see down here that there's also spatial variation in this eastern part of northern Namibia. And this is a further zoom. So you'll notice that we're only estimating incidence rate where the population exists, which is different to before. And that there is spatial variation. So in Kavango here, the rate seems to be lower than in the eastern part of Namibia. We can also estimate the uncertainty because we're using a Bayesian inference. We can provide credible intervals around our estimates through space-time. And this is interesting. You can see that in the seasonal profiles for each of the different districts in Namibia, when the incidence rate is high, there's a large difference in incidence, whereas they all tend to reduce down to a similar incidence rate in the Northern Hemisphere winter, and then increase differentially in November and December. And this plot here on the right-hand side shows you the credible intervals around our estimates of the population at risk. So you can see, you get a sense of how certain we are of the estimates. So sometimes people want the downscaled maps, and that is useful, but from an administrative point of view, that might not be so usable. Some people can use maps, other people might need different ways of presenting the information. And I found this to be a very useful way of presenting the information. So in order to do this, the pixel level estimates have been aggregated up to the different regions and the different districts. And I found this really interesting because just to explain, the four squares represent incidence rate greater than 10,000. Sorry, incidence greater than 10,000. 3 is 5 to 10,000, 1 to 5,000, and so on, down to less than 500, and you get no blue squares at all. So for a region like Kavango, it's interesting that the cases are occurring primarily in Rundu and all the way through the year. And you kind of wouldn't have known that if you had only the region level information. Whereas for Omusati, and we pointed that out at the beginning, that's the area in the north of Namibia, there are more districts that actually have a high incidence through the year. So I don't know how to say this, but Okahayo has very low incidence through the year, but the other three districts have a high incidence rate through the year. So I think this is a different way of presenting the information, and it's important to remember that this is done through aggregation of the downscaled estimates that we were able to provide. Does that make sense? So you had to go through that step in order to aggregate and get these counts out. Okay, and then this plot, this map, this table rather, shows you the estimated population count, both as a count and as a percentage, at different malaria incidence levels. So if you take Kavango, then there are 60,000 people who have there are 60,000 people counted that have a likelihood of incidence greater than 1, or 31% of the population. So that's a very high number, and this is important in relation to pre-elimination thresholds for malaria. So understanding across northern Namibia whether the country is ready for, has reached pre-elimination thresholds or not. This table can help a lot So for most of the regions, the counts and the percentages are low. But for Kavango, there are a lot of people who are expecting an incidence rate greater than 1 in 1,000. And that can only be done by estimating the pixel level map and then aggregating backwards, in a sense, to get the counts. Okay, so that's as much as I really wanted to say. The important points are that the data sets that are available now for many countries across sub-Saharan Africa are presented through different organizations, and they're readily, as long as you sign up, then you can download them and analyze them. So I think a data revolution has taken place. And when you think that these are the disease and the case data for, the best part of a continent, and similar processes are occurring in other parts of the world, this represents a really unprecedented opportunity to make a difference. There are lots of problems with the data, but we've tried to address those in a systematic way through the statistical modeling. And for the future, I think there are lots of different ways of doing the downscaling, so that's of interest from a technical point of view. If you noticed, we did the Bayesian inference, but the denominator part of the equation was fixed. We just estimated it and plugged it in, so it isn't really treated in the same way as the rest of the model. So that's something that we always wanted to do, was to integrate the denominator or the catchment population part and allow uncertainty in those estimates. We haven't really done that. I think another thing that will be of interest is forecasting. So as these data become more real time and are fed through in a way that allows updating, then that would open the possibility for forecasting in the future, in the near-term future, in order to sort of anticipate what's happening as a function of drivers like rainfall drivers, seasonal drivers, knowing what's happening in situ with vegetation, for example. These sorts of things would allow pushing these maps from the past to real time and then into the future, which I think would be a big step forward. Thanks.